Section 12.6, Triple Integrals and Cylindrical Coordinates, Video 6. In the previous video, we had set up a picture for a triple integral that was already set up for us in rectangular coordinates, putting it in a red box so that you can see it from the picture here. We used the limits of integration to sketch the solid and determine the region in the xy plane, and we're going to redefine both of them in cylindrical coordinates. There is one comment I want to make in case you were wondering. You'll notice when I write my z's, I always write a short horizontal line through the middle. That is simply so that I know it's not a 2. So this is a 2, that is a z, which is important here because the equation says z equals 2. The solid was bounded on the top by the plane z equals 2, and on the bottom by the cone z equals r. The projection in the xy plane was just a circle of radius 2, but we haven't defined that in terms of polar coordinates yet. Not that hard to do. A circle, and technically I should say a disk. A circle is the boundary around it. The disk is this boundary in the interior. So the the polar representation of this disk of radius 2 is the radius is between 0 and 2, and the angle can go between 0 and 2 pi. Remember, you never want to make more than one revolution in polar coordinates when you're doing calculus, because otherwise you're going to overlap yourself. The region's going to overlap itself, like a spiral cut potato. All right, so let's set up the triple integral in polar coordinates. Let's start with the z. Actually, let's start with the integrand. The integrand is x squared plus y squared, and in both polar and cylindrical coordinates, that's equal to r squared. So, pretty easy integrand. Let's go ahead and pick up the r, because we know we're going to need it when we do the double integral in polar coordinates. So dr d theta preceded by an r dz. Now, let's talk about the z's. It's pretty easy now. On top, z equals 2. And on the bottom, z equals r. Now let's do the dr integral. Now we're doing the double integral in the xy plane. On the surface D, the r is bound between 0 and 2. And the theta, also in the xy plane, on the surface D, the theta is allowed to go from 0 to 2 pi. This suddenly became an easy problem. I'm going to do what I've typically done. And when I teach Calculus 3, I usually tell students to focus on one integral at a time and not worry about the other ones until you're ready for them. So let's focus on the inner integral, the integral of r cubed from z equals r to z equals 2 dz. And again, I'm just writing z equals for emphasis. We're integrating with respect to z, so with respect to z, r cubed is a constant. Its antiderivative is r cubed z, and that's being evaluated from z equals r to z equals 2. So if we substitute 2 for the z, we get 2r to the third power, minus, if we substitute r for the z, we get r to the fourth power. So there's the value of the innermost integral. So now we can focus. Let's go ahead and reset the double integral. 0 to 2 pi, 0 to 2 of 2r to the third minus r to the fourth dr d theta. And now let's focus on the dr integral. This will be really easy after this one. After this one, this will be a constant, and integrating it with respect to theta, piece of cake. So the integral of 2r to the third power minus r to the fourth power is 1/2 r to the fourth. You might want to double check that antiderivative. If you need to put some more effort into getting there, that's what you do. Minus 1/5 r to the fifth. And this is being evaluated from 0 to 2. I could write r equals 0 to r equals 2, but r is the only variable. So if I substitute 2, we get to the second half, if I substitute 0, I'll get 0, so I'm not worried about it. I just got to substitute the 2. 2 to the 4th power is 16. Half of 16 is 8. 2 to the 5th power is 32, so 32 fifths. So that's 40 fifths minus 32 fifths, which is 8 fifths. And now, for the final integral, which should be a quick one. Integral from 0 to 2 pi of 8 fifths d theta. 8 fifths theta is the antiderivative from 0 to 2 pi. If I substitute 2 pi for theta, I'll get 16 pi over 5. Minus, if I substitute 0 for theta, I'll get 0. So 16 pi over 5 minus 0 is 16 pi over 5. Again, without the change from rectangular to cylindrical coordinates, this integral would have come to a screeching halt. Although I guess you could have actually done the z integral as is, because it wouldn't have been hard to do here. This is a constant, so stick a z on it, 2 in this. And at that point forward, you would have a double integral, which if you didn't convert to polar coordinates, it's over. So I guess you could have actually waited until you'd done dz and then gone straight polar instead of going cylindrical, which is just polar in 3 dimensions, prior to integrating with respect to the z. All right, tricky. I'm going to pause this video and find one more problem in the homework section because I feel like these problems could really do more I could do more justice to these problems with one more example.